Okay, let's unpack this. Imagine, right, a seemingly simple element, something scientists figured they had a pretty good handle on,
Yeah.
and then suddenly it reveals it's been hiding this uh, pretty big secret for 2 decades.
Wow.
That's
Okay.
what we're diving deep into today, this exact kind of mystery involving the element bismuth.
Ah, bismuth. Yeah, it's a really fascinating case. It shows how even in fields you'd think are pretty well mapped, like material science,
Mhm.
well, nature can still throw you some curveballs, especially if you look closely.
Exactly. For years, bismuth was just, there, it seemed pretty average. But experiments kept hinting at something extraordinary,
Mm.
something that the basic theory, the rule book, said it shouldn't have.
Right.
And our source today, this report on SciTech Daily about some really cool research from Kobe University, seems to have finally cracked it.
And what's really exciting here, I think, is that it's not just about bismuth, this whole puzzle.
Right.
It ties right into this critical group of materials for future tech.
You mean the topological materials?
Exactly
Yeah.
those,
Got it.
topological materials.
Yeah, they always sound a bit sci-fi to me. For listeners, maybe folks who aren't, living and breathing condensed matter physics daily,
Mm.
what makes a material topological?
Okay, good question. Think of them as having this sort of split personality.
Okay.
Inside, in the main bulk of the material, they're insulators. Electricity just doesn't flow through, dead stop.
Right, insulating inside.
But then, get this, on their surface, or maybe their edges, they suddenly become perfect conductors, like perfect.
Whoa, okay, insulator inside, perfect conductor outside.
And here's the really wild part, that surface conduction. It's incredibly tough, robust. You can mess up the surface, throw impurities on it, introduce defects.
Yeah.
And that perfect conduction just keeps going. It's protected by the material's fundamental topology, its basic structure.
So, basically useless for conducting inside, but a superhero conductor on the outside, and it's tough against flaws.
That sounds incredibly useful. Precisely. That weird combination, that duality, makes them prime candidates for, well, revolutionary technologies. We're talking potential building blocks for things like quantum computers,
Okay.
which need these super reliable paths for electrons, or maybe spintronics, using electron spin, not just charge, for computing. Big stuff.
Huge implications, yeah.
Yeah.
Okay, but back to bismuth. If these topological materials are so special, and bismuth just looks, well, normal, where was the problem? What was the disconnect?
Well, for a long, long time, the theorists, the physicists, looking at the basic properties of bismuth, its atoms, how electrons line up.
Fundamentals.
Yeah, the fundamentals. The calculations kept coming back saying, nope, bismuth shouldn't be topological. Its bulk properties just don't fit the profile.
So theory was clear. Bismuth is not one of these special guys.
Right. Theory said no, but then the experiments. People doing measurements kept seeing signs, hints of topological behavior, but only at the surface of bismuth crystals.
Ah, okay, so measurements showed.
They measured conductivity, they saw how electrons behaved, and it looked topological. It just completely contradicted the theory. So you ended up with this, 20-year puzzle. Theory says no. Experiments seem to say yes, or at least maybe just on the surface. How could that be? Was the theory wrong? Were the experiments misleading somehow?
And that is our mission in this deep dive today. We're going to use this Kobe University research, the stuff covered on SciTech Daily, to unpack how they finally resolved this.
Yeah, what surprising new physics they stumbled upon.
Exactly. And what it means for material science overall. It's a great reminder that even on paths scientists have walked many times, there are still these deep secrets hidden.
For sure.
And speaking of discovery, if you're finding this journey into the quantum world as fascinating as we are, please do take a second to like this, subscribe to the Deep Dive channel. If you shop online, using our affiliate links is a huge help, genuinely supports the show.
It really does.
And hey, if you've read something cool, some complex topic you want us to unpack next, drop a suggestion in the comments. We love getting those.
Oh.
All right, so this puzzle has been around for ages. How did the team at Kobe, especially the lead researcher, Dr. Yuki Fusaya, start to pick it apart?
Well, the source really highlights Dr. Fusea's unique relationship with bismuth. He's a quantum solid-state physicist, and apparently he's kind of a bismuth lover.
A bismuth lover. I like that. That's some serious dedication to one element.
Isn't it? And he's been studying it for a really long time. His motivation, as he puts it, was simply wanting to know everything about it.
Just pure curiosity.
Exactly. And it turns out that broad, deep dive into all of bismuth's properties, not just laser focusing on this one topological puzzle, that's what let him spot something others might have overlooked.
Okay.
Because he was looking at so many different angles, he was the first to really identify this subtle thing happening right at the surface of bismuth crystals, often ignored.
And what was that? What was the clue?
He found that the crystal structure, the way the atoms are arranged, it isn't perfectly the same all the way through. Right near the surface, the atoms settle into a slightly different pattern compared to deep inside the bulk. He calls the shift relaxation. Think of it like the outer layer of bricks on a wall maybe settling slightly differently because they don't have bricks pressing in from all sides, just from the inside.
Okay, so the actual atomic grid, the lattice, is physically different right at the surface.
Exactly. A subtle but real physical difference. And this tiny structural change, that sparked Dr. Fusea's big idea. He started wondering, could this surface relaxation, the slight tweak in the structure at the boundary, could that be why the experiments looked weird? Could it be affecting how electrons behave only on the surface, making it look topological, even if the inside, the bulk, really wasn't?
That makes intuitive sense, right? Structure changes, properties might change too. But this idea that the surface could be doing its own thing, so different from the bulk, doesn't that kind of go against a pretty basic assumption in this field?
Oh, absolutely. And that leads us right to the core of their big finding. For years, scientists studying topological materials, they've operated under this guiding principle called bulk edge correspondence.
Bulk edge correspondence. Okay, let me guess. The bulk and the edge, they correspond, they match up.
Small chuckle. Yeah, you basically got it. The principle assumes that those unique, robust things you see happening at the surface or the edge of a topological material.
The cool conducting stuff.
Right. It assumes those are a direct, accurate reflection of the material's true topological nature deep inside in its bulk.
Okay.
It's like assuming if the outside walls of a house look super strong, the internal structure must be similarly strong in the same way. It was like fundamental, made classifying these materials way easier.
So it was a useful shortcut. Measure the surface, know the bulk.
Pretty much, yeah. And look, it worked pretty well for a lot of the topological materials they found earlier. But Dr. Fusea and his team, they suspected bismuth might be where this rule breaks down.
So how'd they test it?
They didn't just guess. They used powerful computer simulations. They modeled how electrons would behave in bismuth crystals. But, and this is the key part, they specifically built into their models that subtle change in crystal structure at the surface.
The relaxation.
Exactly, the surface relaxation Dr. Fusea had found. They were simulating the real physical structure, including that slightly different surface layer.
Got it. They put the physical reality they observed into the math model that used to say, nope, not topological.
Precisely. And the results from their simulations, they were, well, definitive. They showed really clearly that the relaxation of the bismuth surface by itself is enough to create electronic properties right there at the surface that make it look topological in experiments.
Wow. So it wasn't the bulk showing through, it was the surface itself, just because its structure was slightly off, creating its own misleading signals.
That's exactly it. Those topological-like signatures people were measuring, purely a surface effect, triggered by this structural relaxation. The bulk, the inside of the bismuth. Still not topological, just like the original theory said. The surface was essentially, you could say, masking or overriding the bulk's true non-topological nature.
So the surface was lying about the bulk, giving off this topological vibe when the inside wasn't playing along at all.
Yeah, that's a good way to put it. It certainly gives that impression. And by showing how this happens, their study proves directly that this fundamental principle, bulk edge correspondence.
The idea that the surface tells the truth about the bulk.
Right. It shows that principle can be broken. Dr. Fusea actually says in the article something like, until now, the characteristics at the surface represent those in the bulk. However, our study shows that this guiding principle can be broken.
That's a pretty big statement. It challenges something really core to the field.
That's huge. It's not just explaining bismuth anymore. It's saying a rule everyone thought applied to these materials maybe doesn't always. And they came up with a name for this, right? This new effect.
They did, yeah. To describe the specific thing where surface relaxation breaks that bulk edge link and makes the surface look topological even if the bulk isn't. They're calling it topological blocking? Topological blocking. Huh. Makes sense the surface properties are sort of blocking the real story from the bulk.
Exactly. It captures that idea. The surface is, in a way, blocking our view of the bulk's topology, or maybe its lack of topology. It's a new name for a really surprising new phenomenon, and it adds this important layer of complexity, you know?
Yeah.
It means scientists have to be maybe a bit more careful now. Can't just rely only on surface measurements to classify these materials. The surface might not be telling you the whole story about what's going on deeper inside.
Okay, so bismuth mystery solved. It's this topological blocking thing caused by the surface relaxing. But you said this might apply elsewhere too, not just bismuth.
Oh, definitely. While bismuth was the specific case that led them to this, the team really stresses that the basic idea that surface relaxation can mess with the bulk edge correspondence and create these misleading topological signals, well, they think it can be broadly applied to other systems.
Meaning we might find this topological blocking in other materials as well.
It's very possible. Now that scientists know this mechanism exists, they'll likely start looking for it. Are there other materials showing weird surface properties that don't quite match the bulk theory? Could surface relaxation be the culprit there too? It might even mean some materials previously thought to be topological based on surface data might need a second look, just to be sure the bulk is really topological too. It adds this extra check you need to do.
So it could lead to a reevaluation of some materials, or at least demand like tougher experiments to really confirm the bulk properties.
Exactly right. As Dr. Fuseo points out, the most important thing in topological materials science is to get the topology of matter right. You need to know for sure what you're dealing with.
Makes sense.
And this discovery, it highlights a new way that nature can kind of, well, deceive us about a material's true bulk state. So this research is super important for correctly identifying and classifying materials that are genuinely suitable for those advanced applications we talked about.
And I remember seeing something nice in the article about bismuth's track record in physics.
Yeah, there was a nice note on that. Dr. Fusea mentioned that bismuth actually has this history, It's often been the material where some really fundamental physics effects are discovered first, and only later do they find those same effects happening in lots of other substances.
Ah, so it's like a proving ground.
Kind of, yeah. And he seemed personally pretty happy that, another phenomenon first discovered in bismuth has been added to that list. A bit of personal satisfaction for the bismuth lover.
That's a great little detail, a fitting chapter in bismuth's story. And for anyone wanting the nitty-gritty, the paper was published in Physical Review B, May 15th, 2025.
Yep, definitely a significant paper for people in this area.
Okay, so let's boil this down. What are the absolute key takeaways from this deep dive?
All right. First, bismuth itself. That 20-year puzzle, solved. We now understand it's not actually a topological material in its bulk. That settles the old theory versus experiment fight.
Okay, and the reason experiments look topological, that was because the surface of bismuth has this slightly different crystal structure, the relaxation. And that change makes the surface act topological, even though the inside isn't.
Exactly, and this whole effect, they've named it topological blocking. Big deal because it shows that surface properties don't always reflect bulk properties. It breaks that standard bulk edge correspondence rule scientists used to rely on.
Right, a fundamental principle challenge.
Yeah.
And lastly, this isn't just a bismuth story. This topological blocking idea could apply to other materials too.
Yeah, which means scientists need to be more careful, maybe use more thorough methods when they're identifying and classifying potential topological materials for all those future technologies.
Got it. So we kick off this deep dive with this decades-old mystery about bismuth seemed ordinary, hinted at extraordinary. And we've landed on the discovery of a totally new phenomenon, topological blocking.
Yeah, one that not only solves the bismuth riddle, but also makes us question a basic assumption in material science, that the surface is always a reliable window to the inside.
It's really a powerful reminder, isn't it?
Yeah.
That even in areas we think we've got figured out, the real world, down at the atomic level, can still hold these pretty surprising twists.
Absolutely. And understanding these really subtle effects, like what happens right at the surface, is clearly going to be critical.
For sure. Especially if we want to actually unlock the potential of these advanced materials for things like quantum computing, spintronics. Getting the fundamental properties right is step one. This research really helps with that.
It really makes you wonder, though, if surface effects can be this significant enough to hide the true nature of the bulk, what other materials might be doing something similar?
Good question.
Are there other simple rules or guiding principles in physics that might start to fray at the edges when we look really, really closely at the complexity of reality, especially at these boundaries between different regions?
It definitely raises some big questions about how we investigate matter, the limits of our models maybe. Well, this deep dive into bismuth and topological blocking has certainly given us, and hopefully you, a lot to chew on.
Hope so.
We hope you found it insightful. Please remember to like, subscribe, maybe click an affiliate link if you're shopping. It helps us keep doing these deep dives. And definitely tell us in the comments what complex topic you want us to unpack next time. Stay curious.